Okay, with that, here is the outline of the BAA, which I understand you don't have. I apologize for that. We're always in a race. We have to announce these things a month ahead of time, and then we're in this race with the bureaucracy to get the BAA out. It should be out very soon. I'll let Mark say anything more specific about that when he gets up, but we hope in a day or two. Here's the outline. As you all saw, we do have this concept paper, which of course is not the binding BAA, but really describes the technical background and gives you kind of the broad strategy of what we want to do in the program. I'll walk through the briefing, give you that background, to also have slides with a lot of the more specific information that's in the BAA that I can go through today. And this is a 6-1 basic research program, especially because of DARPA's AI Next initiative. A big part of that strategy is to kind of go well beyond the state of the art of AI. Other parts of the strategy are to do AI applications for DoD, but this is one of the components where we're really looking for, revolutionary, groundbreaking, high-risk basic research. So that's the nature of this program. So here's the problem. As many of you know, common sense has been the elephant in the room in AI for a long time, right? I can remember John McCarthy wrote a paper about programs with common sense in 1961 or 2, right? And in the early days of AI, I thought it was going to be easy, actually. Just encode some knowledge into a computer and it'll have common sense. And that ended up being incredibly difficult. So it's a problem that's been around for a long time. It's a large, difficult, unbounded, slippery problem that we're trying to work with. Well, I think it's one of the biggest barriers between kind of the very narrow AI applications we have today and the more general AI systems we'd like to build in the future. Today you either carefully program a system for a specific problem, or you carefully train it with a huge amount of training data and generally labeled examples, so you've built a function that knows just how to compute that one particular task. And so we're trying to get beyond that by creating a more general capability for AI systems to use. So I've kind of depicted that here as a common sense server, which is kind of a very general term for that, but meaning you've got some kind of service that's going to take natural language questions, provide answers, take questions though in images and natural language, not in a very specific, formatted ontology or that sort of thing. So we're trying to make it general in that way as well. So that's the overall goal. Here's the problem statement, goal statement for the program, right? That we develop this common sense service to enable applications to understand new situations, monitor the reasonableness of their action, communicate more effectively with people, and perform transfer learning. So they're just, if we have any kind of general common sense service, it's going to be useful for almost every imaginable AI application. But these 4 use cases, or ones in particular, do situation understanding, monitor the reasonableness of your actions, communicate with people who every time they communicate it in terms of common sense, and then use that common sense base to more effectively transfer learning to new domains. So what is common sense? Of course, that's one of the slippery parts of this program, this problem. It means a lot to different people. It's really unbounded. The closest thing you come to a definition, I think, is what I have here in Wikipedia, or John McCarthy's version of it in predicate calculus, which is basically common sense is what every person knows, right? So you have an average adult human, if he knows something without debate, that's kind of common sense, right? John McCarthy wrote that in logic by positing there's an agent we'll call any fool. Any fool knows exactly what everyone knows. So if he knows something, that's common sense. That doesn't give you the specifics of what it is, but kind of gives you the gist. So for this program, we're kind of using 2 very different definitions of it, which are below that. One, I tend to think of, and a lot of people tend to think of common sense, is three broad topics. One is intuitive physics. That's certainly a big part of it, right? We have people, even children, have a very rich knowledge of the physical world, right? And they're not doing precise Newtonian calculations and using a physics engine to do that, but you really can understand how objects work. If you throw something, it'll be across the room, right? If two objects hit each other, they're going to interact in some way. If an object's not supported, it's going to fall to the ground, right? So just this very rich general understanding of physics is an important part of common sense. Similarly, this intuitive psychology or folk psychology, very basic general understanding of why people do what they do, what people's goals are. If they walk into a restaurant, that probably means they're hungry. You know, these kind of general knowledge that enables us to understand a huge amount of what's going on in the world without having very specific knowledge of individual people or situations. And then the third part of that is just common facts, the kind of things you'd find in Wikipedia, you know, or you could Google facts, you could Google kind of general knowledge about the world that everyone has. So that's one definition, those three categories. The other definition we're going to use for part of the program is to look at what we know about, from developmental psychologists, about what young children know about the world, infant common sense, if you will. So we've highlighted as an example of that, psychologist from Harvard, Elizabeth Spelke, who has spent years doing research on what she calls the core knowledge systems or core domains of childhood cognition. And these are the six, core systems she talks about: objects, agents, places, number, forms, and social beings. We've decided in the program to focus on the top three: objects, which is intuitive physics; agents, which is intentional actors, which includes people. So that's kind of the beginning of intuitive psychology, of theory of mind, but also includes external forces that might act, in the scene. And in places, which is spatial reasoning. So intuitive physics, intentional actors, and spatial reasoning, are the kind of core domains of common sense we're going to work on in that track. So, as you probably recognize, we're going through the Heilmeyer Catechism that you're probably all familiar with. So how is it done today? There's this great survey paper by Davis and Marcus, came out in 2015, kind of used as a reference the history of all the things people have tried, to develop, to work on common sense, and a lot of different approaches. Some of them logic and knowledge-based, some of them based on machine learning, some of them on crowdsourcing. So it's been a problem that people have worked on for a long time in AI. Kind of the granddaddy of the first generation techniques was the psych system, where I worked for a few years and know well. And it's an incredibly impressive effort. This is one of the first wave, as we call it, AI people. Doug Linnett, who in 1985 left Stanford to go off on a 35-year effort to encode everything you'd consider common sense in a logic, a knowledge base. And this is just the sketch of the ontology of what's there, as well as a lot of rich reasoning procedures. So he kind of pushed that technique, to it, and he's still working on it, right? But somehow it never quite works, right? It doesn't really provide the general common sense capability we'd like to have. I'm not quite sure why. Doug would say, well, he just hasn't been at it long enough. He needs another decade and this will work, right? I tend to think it has a lot to do with the brittleness of the symbolic logic representation that's in the system. But it is a great example of, what people have tried to do to build up a common sense knowledge base. So what's new, kind of is the next part of the Heilmeyer Catechism. Why do we think we can go beyond that? And so these are four kind of examples of some of the progress that's happened in recent years that I think will be useful nuggets in putting together this next attempt to build machine common sense. I think one of the biggest deficiencies, the logic approach, is you didn't have representations that are grounded in perception, and grounded in kind of more flexible representation techniques, such as embeddings, which is, of course, one of the new, big techniques that's come out of deep learning. There are other kind of probabilistic, models that give you a much more flexible representation, but I think that's an important element of it. Of course, that has to be combined with reasoning in some way, and probably means you have to have a combination of those techniques. But I think just doing it in a purely symbolic way is never going to give you the flexibility you need to solve this problem. Now we turn to this next one about learning predictive models. A lot of people are now using this self-supervised technique, especially in the deep learning community. They can watch a video, watch an experience. The only training signal is predict what will happen next. And just by doing that with a lot of labeled training, without labeled training examples, they can learn a model of phenomena, that a lot of it would work to give you a model of common sense. Similarly, down at the bottom, there's been a lot of efforts over the years with kind of increasing sophistication to use machine learning techniques to just mine the web, mine videos, mine images to extract common sense. And I mentioned the NEL program at CMU, or its companion project, NEAL, which is actually mining common sense from images and video. And then finally, this other line of work, which I've already mentioned, is there's been a lot of work in developmental psychology to get much richer models of what's happening in childhood cognition. So I think that's going to be an important cue to help us, especially with one track of the program. So those are some of the nuggets that, I think are glimmers of hope. This is not a precise description of exactly what you have to put in your proposal. It's always an important idea to just show there's some new ideas out there. And in the paper that we sent out, I've put in a lot of references. As a caveat, that doesn't mean those people have to be on your team. It doesn't mean those people will get a contract. If I referenced you, it doesn't mean you're going to get a contract. I've had people say, oh, well, you referenced me in the BAA. Why did I not get an award, right? So it just doesn't work that way. I'm trying to provide a survey of some of the interesting nuggets I've seen, but I'm really looking for interesting, kind of innovative proposals on how to put these techniques together or others to solve the problem. So here's the broad approach. Now like I say, this is a large, slippery, kind of unbounded problem. Biggest part of our task at DARPA is to figure out how to focus it in some way, right, so we can make some kind of progress. So these are the two challenge areas, if you will, that will end up being the two, broad technical areas we'll be asking for. So one of these is what I'm calling foundations of human common sense. So this is where we'll look heavily at what the developmental psychologists are telling us about the cognitive systems that children have, especially from 0 to 18 months old. That's kind of the target range we're looking at. Where at 18 months, children have pretty rich understanding of objects, agents, and places. They're beginning to understand language and put language labels on those concepts, but they're not yet in full-blown, language generation. So that's one where the task is to build a simulated common sense agent that can take tests, which I'll describe in a minute, that show that exhibits, the common sense of an 18-month-old. Now, the second approach is very different. Now we want to go after broad common knowledge, not restricted in any way to what humans do or what children do, or don't involve psychologists in any way unless you want to. And here I'm envisioning people will do things along the lines of use machine learning, crowdsourcing, manual construction, by whatever means you can, put together a broad common sense service that can answer common sense questions. And for that test problem, we use the Allen Institute for AI is developing a test environment and a set of benchmark tests for broad common sense. We're just going to use those tests as what we'll do for that event. So we have two very broad strategies here. It reminds me of this analogy, which is often used in AI, right? Did the Wright brothers build a plane to fly like a bird, right? And the superficial answer is no, it didn't flap, right? And so there's always this kind of controversy. Should we mimic human cognition to get to AI, or should we just forget that and look at what other artificial means we can? So as you can tell in these two strategies, I'm saying, well, let's try both. But I first want to make the case on why it was important for the Wright brothers to have some information about how birds fly. And that, brings up this kind of little-known German scientist that preceded the Wright brothers, Otto Lithenol, who in the late 1980s spent a lot of time studying stork flight and wrote this exhaustive treatise on how to understand what birds do that gives us insight in how to build artificial machines. And using that, actually built the first successful glider, which eventually killed him on one of his unsuccessful flights. But in the process of that, he produced these tables of lift and drag, which the Wright brothers actually used. They had found they had to revise some of the numbers, but that insight, as you can tell from this quote from Wilbur Wright, was the key idea that enabled them to build the first real flying machine. So in the foundations of human common sense, this is what I'm looking for. We're not going to try to model everything in common knowledge, but I want to study as well as we can the cognition of young children, get all the insights we can from developmental psychologists, see if we can capture in some way intuitive physics, intuitive psychology, spatial reasoning that mimics kind of this magic that happens in just a 1-year-old has more common sense than any AI system we have today. So that's the motivation of that approach. So to do that, as I said, I picked this one example of Elizabeth Spelke, a prominent developmental psychologist that has, studied these core systems. There's an extensive amount of research on it. There certainly are other developmental psychologists that have different variations of that, but they almost all agree that certainly objects, agents, and places are prominent cognitive systems that young children have, and I'm really trying to do whatever we can to mimic some of the important characteristics of those systems. So this is an interesting thing I've discovered in that the developmental psychologists, one of the reasons they have this new information, they've got these incredibly interesting techniques to understand childhood cognition even before children are verbal, even before they can ask them questions. And this is one that MIT Childhood Cognition Lab has where they actually crowdsource studies with 12 months old and 6 months old. And this is how they do it. They create videos that they'll show the child. You see on the right here, the parents who sign up for this study hold their infant on their shoulder, so the parent is not looking at the video, not giving any cues to the child about what's going on. The child watches the video, and then they'll see things like a ball rolling up a hill or a ball rolling down a hill, and they can tell from the expressions on the child whether that violated their expectations or not. So just an example of incredibly interesting array of techniques developmental psychologists now have to study this, which has produced a pretty impressive array of results that we're going to use as kind of inspiration for studying these core systems. So these are for each one of those 3 core systems, objects, agents, and places, some of the key, cognitive abilities that they've observed that children have. The schedule kind of shows when they occur, right? Now, I'm not interested in duplicating this developmental sequence, but I am interested in saying, okay, look at the capabilities that an 18-month-old has. There's all these studies that are referenced in the document and in the BAA on how psychologists have studied that and what they found, and I want people to try to duplicate those capabilities as best they can. And so again, here's some videos illustrating objects and agents, right? And it's not just, look at objects. They're all the things that are going on as a child understands the physical world. This is not only does he understand the physics, but it's the basis for all sorts of concepts. Here's sequence. Look at the sequence of blocks that he's putting together there. Understanding causality, understanding all these kind of rich ideas that have been difficult for AI to capture. If we can capture something of what's happening in that basic system, I think it's going to give us, some real insight in how to do it in computers. The one on agents there is interesting. Of course, here's a young child. One of the interesting discoveries there is young children will judge the importance of an action by an adult by how much physical energy is exerted. So these systems interact. So here the child can see Alan Alda straining to move these books all the way across the room, infers his goal is to open that door, and then helps him out, right? So I think that, one, there's a lot of important capabilities that you get from mimicking these systems, but the hope is you can capture some very general intelligence capability by mimicking these that enables you to build up to much richer AI systems. So now I want to give you a nice example from my personal life on how these systems interact. These two adorable people are my two grandsons. This is Quinn, the smaller one, who just turned 1 year old. That's kind of our, he's our target, Brooks is the older one there, who is his evil brother, who, of course, treats Quinn like every chance he gets. And so Brooks has stacked up this stack. Quinn, using his agent system, can tell this must be important to Brooks because he spent all this time doing it, and then uses his object system to have his revenge. So there's interesting interactions of these systems. So how will we measure that, right? This is a pretty slippery, this is not going to be an easy task. There's actually a separate technical area to get some high quality people to do the evaluation of the childhood cognition track. So this is how I'm envisioning that happening, is doing testing from at least two different sort of environments. As you can see at the top, these videos are the kinds of videos they show children. In one case, the ball will mysteriously disappear. In the other case, it stays permanent, right? These are the kinds of characteristics that were listed in that table. They find out about these with children by just showing them these videos, and you see which ones violate their expectation. So the first range of tests will just be, see if you present this to your computer system, get an expectation signal out of the system. Does it have the same violation of expectation behavior that an infant does? So that's kind of round one, and actually, I think there's a paper I cited, or in the concept paper, where people at DeepMind have already used this exact technique to try to measure the quality of their intuitive physics engine. So that's round one, right? And then we'll do much more richer tests and probably some sort of simulated 3D environment with accurate physics, right? I use this example of the Thor system that the Allen Institute for AI has, but it's up to this developer who's going to develop this test to pick the best simulation environment to use. So then the next level of tests will be, you've got your simulated AI system will go into this environment, be given a variety of experiences. And I'm envisioning the test to be of these three types. The first, which I've described, is just look at their expectation, right? Their violation of expectation signal match that of what you observe, in the childhood studies. Next level will be, I'll call, experience learning. So now you have the simulated agent. It's in this simulated 3D world. You present a new object or a new agent or a new place or a new combination of those, and see if the agent appropriately learns kind of new properties of that or how to interact with it. And learn that from a dozen experiences, not from 1,000, but just from a few experiences, see if they can learn, as a child would, important properties or how to interact with that. And a final level would just be more complex problem-solving tasks. Maybe given a goal object they've got to find, or there's a set of things that might be used as a tool. They've got to figure out how to use that to achieve some goal. So those are the broadly the three levels of testing we would do. the precise definition of these kind of will be up to the evaluator, right, in TA2. So to measure that, we're just going to have, here we have our list of, our initial cognitive capabilities. And I should mention this is just an initial list, again, that the evaluator in TA2 would take as a starting point and really work on to revise. All of these references here are the different studies in developmental psychology that report what they've observed from children for each one of these capabilities. And so for each one of these 3 levels of task, violation of expectation, experience learning, and problem solving, when we do the evaluation, it's really just a pass-fail. We'll do some assessment of, does the simulated cognitive system exhibit, behavior that's close enough to what human children do, and that will involve, some judgment. It's very difficult to turn that into a precise, objective metric. But that's the strategy. I had to add some target milestones, okay, to get this through. So these are, as often the case, you just kind of pulled these out of the air, right? Kind of guessed at what would the progress be over the years. As I've said clearly in the BAA, and I think I've got the quote later on, there are no go, no-go decisions in the program. These metrics are not being used as the sole reason to down select someone or to make funding decisions. They're just there to have some way to measure progress. So that, I think it is worthwhile to have some kind of goal. You got to have some way to know, did you do better today than you did yesterday? And kind of that's the spirit of these things. And we'll do the best we can to get some sort of measurement on how close these systems are coming to childhood cognition. So now we'll shift to the other area, where we're looking for people to build systems that will have broad common sense. I'd kind of mentioned these examples earlier. There's a lot of, work actually going back to this NEL system, which is several years old now, but a whole kind of explosion of new work in the new fields of AI, where people are using a lot of interesting techniques to mine the web, mine all sorts of experiences to see if you can learn kind of common sense models of some kind of what's going on. And so, as I mentioned, the test problem for that will come from the Allen Institute for AI. And as many of you probably heard, Paul Allen just passed away this week. Which is sad news. I worked there for several years, and he's tried to do a lot for AI by establishing this institute. Although the institute will continue, that's not going to stop. I imagine that there's some sort of endowment to go with it. But Orrin Etzioni, the director, has assured me that's going to continue on their 10-year plan. So that's going to be around. So one of their prominent goals they've just created is to have a set of benchmarks and tests to measure common sense. So these are the 5 tests that they're developing. The first one, this common sense natural language inference test problem, is out there on their leaderboard. I'll show you the web reference in a minute. The other 4 are in development, but will be developed before the program starts, and there are sample questions for each one of those out there. So the basic idea is, in both the first 2, the common sense natural language inference and common sense NLI with vision, is based on, they develop these through a pretty elaborate crowdsourcing technique where they take scenes from movies. There's a commonly used movie database they used, grab scenes from it, then had people crowdsource common sense questions about what's going on. They even run it through kind of an adversarial check to make sure that it's a multiple choice test. You get the question in natural language. The answer is to select the multiple choice answer. They even have an adversarial step where they check to make sure the answers don't give away some subtle cue that's easily recognized by a deep learning system, which is what can often happen in these cases. So they've, done some, gone to some extent to defend against that. And so anyway, so that's the first one. The second one is the same thing, although instead of a natural language question, the question is the image itself. And you've got to look at the image and understand what's going on. The third test will be on abduction. then one on physical interaction and social interaction. So hope to have tests of all the items in those three bubbles that I talked about earlier. And they will be creating a kind of a sequestered test environment where they'll have the infrastructure available where you can see a bunch of sample data and sample answers to train your system if you want to do that, or not train if you don't. But then when it comes time to actually do the test, your code is delivered to this system, in a Docker-like framework. They administer the test with test questions that they keep sequestered and can report the results. So that's kind of the scheme we're going to use. And there'll be some references where you can look up more information about that on their website. So here's our notional target milestones there. We already know, as a part of what AI2 has done in the first one, they've actually measured how effective, a whole set of different learning techniques would be on answering these questions. And is typically, they can get pretty far. They can get about 55% with just machine learning. But humans do this at 88%. Right, so there's that gap, is what we're trying to narrow. I don't think you're going to get to 88% by just the learning techniques, that they've tried first. There's got to be, especially if you look at the broad set of questions we'll have for all 5 of these tests, will be at least a challenging, goal, if not too challenging, but that's what we want. We really want to see how far we can push systems to have a really general understanding of common sense. So here are the actual technical areas. Again, now I have some word slides that are kind of pulled right out of the BAA, which you'll be able to read at some point, and talk about each one of these technical areas. So first, the one, TA Foundations of Human Common Sense. Kind of here's the goal that I've described. We will want to have multiple development teams in each category. Now, I know there'll be a popular question is, how much money should I ask for this team, right? And my last BAA at XAI, I gave a number, I gave a range. I got 90% of the proposals were $5 under the top number, right? So I'm not going to do that this time. I've been on your side. I know you got to have some idea what the ballpark is, right? So I've got these 2 big technical areas and the third one for the evaluator. So I'm expecting something like 3 teams in each of these 2 broad areas, 1 team for the evaluator, and there's some kind of roughly $70 million for that, right? So that probably gives you too much information already. Everybody can divide by 7, and now they know what the target number is. Although now I really am interested in what's needed to solve this problem, right? You know what I mean? I know it's vague, it's kind of mushy. The more you have, the better. But I don't want to throw out a number that's too precise and have people artificially pad or artificially cut resources from it. I'm really looking this is an important problem. DARPA really wants to make progress on it. I want the best team you can put together to solve that problem. And then you'll kind of have to do the game theory on, if that's the average number, is mine so much better than the other guys it's worth, extra, or is this an interesting little niche thing that might be worth it even though it's a smaller amount? That it's impossible. I don't know how to advise you on that part of it, but I kind of give you a ballpark of what money's available. I'm really looking for teams that can solve this problem. So, and I am neutral about what technology is used, so I know this is going to involve a combination of a lot of techniques. I, mainly because I spent 2 of my DARPA careers funding symbolic AI, I'm a little bit jaded on that because, it never turned out as well as promised. But it doesn't mean that that's a non-starter, right? I do, though, certainly expect whatever you're doing has got to be a mixture of current AI techniques, but that's up to you. I really am neutral about that, and I'll want a range of techniques proposed. I want a range of techniques, that I select in the program, so they won't all be, the same one. So in this track, I am expecting each one of the teams to have a developmental psychologist on the team, right? I think it's important here that, you are informed by what happens in childhood cognition. This is the one we're trying to get at. What are the properties of lift and drag that happen in a stork that make it possible for an artificial machine? I really want to know what are the key insights we get out of childhood cognition that help us build an artificial system. But given that, I think I'm open to a range of how heavy do you go in on developmental psychology? I know you have to at least have a developmental psychologist on the program that's going to provide that, or on the team that's going to provide that insight. I have other teams on the other end of it will not only want to have a developmental psychologist or two, they might want to actually do developmental psychology research to test their system or to inform their system. I'm open to both ends there. I think the minimum requirement is you have some developmental psychology expertise. I'm open to how deep you go into that, although I don't want it to be just a developmental psychology research project. Anything that's done in there has to be in service of understanding and developing the computational model. So that's where I think with the psychologist, I think part of the program, a secondary goal is to kind of consolidate the theories of childhood cognition and pull out of that what's useful for the artificial system. The next bullet, as I've already mentioned, you can have optional companion research experiments in developmental psychology that are really important for informing your model, but those are optional. This is true in both tracks. Our evaluator will provide some sample data, some sample problems, the simulation environment that you work in, but it's really up to each team to figure out how they want to train this system. I know I have people on very different sides of the nature-nurture continuum here. Some will say, well, children, as they do, come with a full-blown mammal common sense system, right? You've got to build in something. Others, you might say, well, that's just the result of a couple million years of evolution. We could just train it, with enough experience to develop that from the ground up. So I'm neutral about that, but whatever building or training regimen you want, that's up to you, but you've got to kind of provide that. When you write the proposal, this is listed in the BAA. Of course, these are things we want to make sure you include, how you're going to design and develop the model, kind of what's your technical approach, what you're going to do about the psychological theories you're working with, how will you sequence the development, kind of what will be your approach to perform those evaluation tasks we sketched out, how at least will you try to achieve the milestones. And it is important that there's a 6-1 program. You do whatever you can to publish, share, distribute the results of the research. I think for this kind of program, we'd like things to be as open as possible. There's not anything remotely classified here. We do want to create a sharing kind of research community. Another one of the big reasons to not have a go, no-go step. You want people to share information and benefit from each other's work. Now for the test environment, of course, here's the goal is to both provide the simulation, video, whatever infrastructure for the tests, and probably more importantly, actually devise the specific tests for these cognitive capabilities. So in that, people proposing to that, to look at those cognitive milestones we proposed as initial ones, kind of give us your, assessment of how you're going to change that, expand it, whatever. Talk about how you're going to devise specific test problems for all of those milestones. Select, modify, or construct your 3D simulation environment. Increasingly, there's a very rich set of those out there. A lot of people are developing kind of very high fidelity simulation environments. We're going with very accurate visual characteristics, with accurate physics, with all these characteristics you need so the agent can learn kind of appropriate common sense behavior in that world. Provide the training and testing infrastructure. again, with sample problems, but you don't have to provide all of the training, experiences for each team. That's kind of up to the teams to do the exhaustive training however they want. If they want to use your environment and run 10 billion simulation runs to train their system from the ground up, the environment should be available, but you don't have to create the training experiences for it. Of course, develop a documentation to give the teams and conduct the actual evaluations. And in both cases, I think it's mentioned later, I'm asking in both tracks for teams to do an evaluation every 6 months. Now I'll move to the second area, the AI2, the broad common sense using the AI2 test problems. Here, if you're proposing to that, again, I'm looking for multiple teams, right? And you can, again, propose here. It's kind of wide open. You don't need any stinking psychology for this one, right? You can just, whatever means you want, artificial, build it, learn it, crowdsource it, just looking for probably interesting combinations of those, or how you're going to build up this common sense repository that can answer the questions. And again, you're not required to have a psychologist involved on this branch. And again, you're expected to submit your problems for testing every 6 months. And there should be, well, I'll mention that a little bit later. We do have these 5, well, I'll talk about that in a second. So again, if you write one of these proposals, we'll be expecting, describe your approach, how you're going to develop these systems, what's your technical approach, how will you sequence the development over the 4-year program, what's your strategy kind of for performing these tasks, what would be your strategy for trying to achieve those targets, and again, how will you publish, share, disseminate, information with the community. So as I mentioned, these are the 5 kind of initial test sets we're going to have on the AI2 leaderboard. As I say, the first one is out there. You can kind of see it, get an idea of what the questions are like. There's data that can be used to train the system or not if you want to. I think there's actually a research paper shows how they developed the test sets. The other 4 will be coming out, in time, certainly by the time the program starts. And another comment here, these will be the initial 5 tests we'll use certainly in year 1, although I think we're open for additional question sets to be added. And I think it's part of, as Orrin Etzioni calls it, wants to have the mother of all test sets on common sense, right? So they may add some. I think it'll leave it open for the performers on the team, especially after the first year. If you want to create your own test set, submit that, and it'd be one though that all the players on that track would have to take. So you can do a little wargaming on I know I can answer these questions and the other guy can't, and you kind of see how that plays out. Now here's the web link, which is in the BAA but not in that concept paper I sent out. But leaderboard@allenai.org, where you can actually see. They have this leaderboard in the testing apparatus with a bunch of different test problems they're doing. Only a subset of those will be the common sense ones. But those are, you can see the common sense natural language inference one there and samples of the other 4. And I think has details on the whole, what's the procedure of submitting your program to be tested and that sort of thing. Here's the schedule. Long way to say, we're going to have a meeting every 6 months. It'll be a physical meeting once a year. The 6-month meeting will be a virtual one, right? I know anymore the most difficult part of these programs is finding a time when all the key researchers you've involved can travel. So I want to try that out. And, module on my schedule, try to get out once a year to visit each one of the performers. You might budget for a couple trips to D.C., especially at the later end of the program. Now, here's on the milestones. Here's the actual wording from the BAA. These are not go, no-goes. We're not going to use them as the primary reason for funding decisions. Now, if you get a 0 for 2 years in a row and you're not showing up for the meetings, right, I'm going to cut the program, right? But if, this is a really hard basic research problem. This is not one where I expect linear progress on these milestones, so they're not being used kind of in that way to kind of arbitrarily cut the budget too soon. I expect some floundering around, especially if you're doing high-risk stuff. Specific deliverables, and you can read this in a paper. There's not anything surprising here. Would like as much as possible for you to have your code available. Understand, we of course always want at least government purpose rights. In this kind of program, it's nice if you can put this stuff on GitHub and, share it with the research community and use the results as a way to synergize, progress in the community. But of course, if you're, from a commercial institution and you've got some initial IP that you want to keep, there's a provision for you to, declare that in the BAA, although we like to minimize that as much as possible. No government-furnished equipment, other than what's involved in the evaluation infrastructure. IP, again, we're, of course, would want at least government purpose rights. Hopefully you make this stuff as open as possible. And then finally, as a summary, here's our goal statement. Here are the dates. We're going to do an abstract phase with the abstracts due November 6th. I think that's a 5-page abstract. And then the proposals are due December 18th. And again, I know that when you're on your side, you're looking for any specific information you can on what does Dave want, who does he want on the program, how much money is it, that's unavoidable, right? But that's not really what we're looking, this is an incredibly hard problem. I've worked on this for most of my life. This is my last program, right? I'm going to retire after this, I hope, and I want to have made some real progress on this, and I want the best ideas I can on how to do that. That's what I want. And if you want to win, that's what, think about that. How can we really change AI and make progress on this problem in a way that really lasts, beyond the 4 years. So with that, thanks.